This video is on the minimum spanning tree problem. Suppose we want to connect a bunch of computer stations together with cables in a minimal way. So I want to connect my computer stations with cables so that all of them are connected, and I want to do it in such a way that the amount of cable used is minimized. So let's say that that's a minimum amount of cable used in this situation. We could think of this as a graph, and the vertices of the graph would be our computer stations, and the edges of the graph would be the edges between computer stations that are connected by a cable. So let's notice two things about this graph. One is that this graph is going to be a connected graph. It's connected, there's just one component. We can take a path from any one vertex to any other vertex. It will be connected by edges. Another thing to notice is that this will not contain any cycles. So this is a connected graph and it contains no cycles. Why is that the case? Well, suppose we did have a cycle in this graph. This is supposed to connect the stations together with cables in a minimal way, and we see that this is no longer minimal. We could remove one of the cables and the stations would still be connected together. And by definition, because this graph is connected and contains no cycles, that means that this graph is a tree. So essentially the minimum spanning tree problem is that we want to find a minimum tree that contains all vertices of the graph. But let's look at a few definitions before we state this problem formally. A graph H is a subgraph of a graph G if the vertex set and edge set of H are subsets of the vertex set and edge set of G. So we see that both H and K are each subgraphs of the graph G. All the vertices in H are also in G, and all of the edges in H are also in G, and the same is true about K. So each of those are subgraphs of the graph G. A subgraph of H of G spans the graph if H contains all of the vertices of G. So we see in this case that K spans G because K contains all the vertices that G contains, but H does not. If H is a spanning subgraph of G and H is a tree, a connected graph with no cycles, then H is called a spanning tree of G. So we see that T1 and T2 are each spanning trees of G. They contain all of the vertices of G, so they span G, and they are each trees, they are each connected graphs with no cycles. So we were interested in a minimum spanning tree problem. And so let's observe one thing. If we look at the number of vertices in the graph G, then we've got 1, 2, 3, 4, 5, 6, 7. We've got 7 vertices in that graph. And let's count the number of edges in each of the trees. There is 1, 2, 3, 4, 5, 6. There should be 6 edges in T1 and 6 edges in T2. And in fact, we didn't even really need to count that. We know from the previous lecture that the number of edges in any tree will be 1 less than the number of vertices in that tree. So any spanning tree of a graph will have the same number of edges. So when we say minimum, we can't mean the number of edges. And we need to add another dimension to our graphs, and that's weighted edges. A weighted graph is a graph in which numbers or weights are assigned to the edges. So we see that the graph G is now a weighted graph. We've assigned numbers to each edge, and those numbers might signify cost or distance or something like that. And so now we can think about which of these trees is smaller than another in terms of its total weight. So in this example, the weight of the graph T1 is the total sum of its edge weights. So the sum of its edge weights is 4 plus 2 plus 6 plus 5 plus 1 plus 3. So we've got a total sum of 10, 12, 18, 21. And the graph, or the spanning tree T2, has a weight W of T2 is the sum of its edge weights, 4 plus 3 plus 4 plus 2 plus 6 plus 1. So its total weight is 10, 15, 16, 20. So these two trees have different weights, and for now T2 has a smaller weight than T1. So finding a minimum spanning tree for the graph G would mean finding a spanning tree for G, a connected graph that is a tree that contains all of the vertices of G, such that the edge weight is minimum. So I'd like you to try this yourself. So try to find a minimum spanning tree for G. And as you're working on that, as you're trying to find a minimum spanning tree for G, can you generalize this? So can you create an algorithm? In other words, can you create a set of steps you would suggest using to find a minimum spanning tree for any graph? So find a minimum spanning tree for that graph, and then think about what set of steps are you using, and can you generalize that as a set of steps that you would recommend to find a minimum spanning tree for any graph. We'll talk about it in just a moment. Okay, so here is a minimum spanning tree for the graph G. It's given by the highlighted edges. And if we want to find the total weight, that's summing together the highlighted edges, and we find that the total weight of this minimum spanning tree is 17. In this case, there is a unique spanning tree for this graph, so this spanning tree is the only minimum spanning tree. In many other graphs, there might be more than one different spanning tree, but all minimum weight spanning trees have the same smallest weight. Typically, when I do this in class, a lot of students actually do come to one of the two algorithms that we discuss. Those two algorithms are Kruskal's algorithm and Prim's algorithm. And as I said, many students do come up with something pretty close to one of these two on their own. So let's discuss these two algorithms and use it on this graph. So here is Kruskal's algorithm. We choose an edge of smallest weight. In this case, the edge of smallest weight would be this edge of weight 1. We then choose some remaining edge of smallest weight out of all the edges that we have not already chosen that does not create a cycle with a previously chosen set of edges. So we can select that edge of weight 2. It doesn't create a cycle. Now we want to continue until we have a spanning tree, or until we have selected n-1 edges. So now I can select any edge that is of smallest weight that does not create a cycle with a previously chosen edge. I can select that edge of weight 3. I could select this edge of weight 3. There aren't any more edges of weight 3 left. The next smallest is 4. But notice at this point, I cannot select this edge because that edge would make a cycle with previously chosen edges. So I can select this edge. It does not make a cycle with anything I've previously chosen, and I can select this edge. It doesn't make a cycle with anything previously chosen. And I now have my minimum spanning tree. I have finished because I have a tree that includes all edges of the graph G. It also has 6 edges, 1 minus the number of vertices in the original graph. So here is Prim's algorithm. Prim's algorithm states that we select any vertex and an edge of smallest weight incident with it. So, as I said, in Prim's algorithm, we start with a particular vertex, and it doesn't matter which one we start with, but let's say that we start with T, and we now choose an edge of smallest weight incident with T. So our options are 6, 4, and 5. Out of those, 4 is the edge of smallest weight incident with T. We now choose an edge of smallest weight connecting a vertex already included to a vertex not already included. So my choices would be that I could connect to Z, I could connect to U, or I could connect to Y, or I could connect to X. The smallest option out of those is to connect to U. Now, next, I'm connecting to a vertex not already included. I could either choose the edge SY or the edge SX. It doesn't matter which one I choose. Let's do SY. And again, one of the vertices I've already included, any of the vertices that's highlighted in yellow, connecting by an edge to any vertex that's not yet highlighted. So I could connect these two. Same deal. I can connect these two, and now I can connect those two. And so I have now made a spanning tree because all of the vertices of the graph are included. One thing to be careful of when you're using Prim's algorithm is that you do not necessarily go from a vertex you just included to an incident edge of minimum weight. We always choose the minimum edge out of all possible edges that join any vertex already included to any other vertex that is not yet included. And by included, I mean highlighted or selected by being incident with an edge. If that isn't clear, I'll try to make it very clear in the next example that we do. On a historical note, Kruskal's algorithm was published by Kruskal in 1956 and Prim's algorithm by Prim in 1957. But this idea actually first appeared in a paper by Borufka in 1926. He was writing about the most economical layout of a power line network, and he both was the first known to have stated the problem and also to give an algorithm that was a solution for the problem. So, unfortunately, these are the two most famous algorithms known, Kruskal's and Prim's, but they were actually not the originators of this problem. So why don't you try one more example? Let's use both Kruskal's algorithm and Prim's algorithm on the graph H below to find a minimum spanning tree or a shortest spanning tree. Because Prim's algorithm starts with a particular vertex, just so that we are all on the same page with our solution, let's do this example starting with the vertex F. So start with the vertex F when you do Prim's algorithm. Okay, so pause, try that out, and we'll talk about it in a moment. Okay, so let's start with Kruskal's algorithm. We can choose an edge of smallest weight. So the two edges of smallest weight each have weight 3. It doesn't matter which one we start with. Let's start with this one. Now we can continue selecting edges of smallest weight that do not create cycles. So 3, 3, 4, smallest remaining weight is 4. Notice I cannot select the other edge of weight 4 because that would create a 3 cycle with what's previously selected. 5 is the next smallest, 6 is the next smallest, and now I am done. I have created a spanning tree. In this case, it happens to be a spanning path of minimum weight. And now let's use Prim's algorithm on this same graph. So we said above that we were going to start with the vertex f. So we're selecting any vertex. We were starting with the vertex f together and choose an edge of smallest weight incident with f. So 4 is the smallest option incident with f. Then we choose an edge of smallest weight connecting a vertex already included to a vertex not already included. So G is already included, but B is not. That is an edge of smallest weight from an included vertex to a not included vertex. Now, out of all the options I have, BA is the edge of smallest weight that meets that criteria. Now, AG is not going to be such an edge because both A and G are already included. So let's look around. What's an edge of smallest weight going from a vertex already highlighted to a vertex not already highlighted? Well, FE is the smallest one. And this is highlighting that idea that we are not always going from a vertex we just included to another vertex. So we are sort of backtracking when we go from F to E. Now again, we're going to select a vertex not already included to a vertex that has been included, an edge of minimum weight that has that property. Here 6 is the only such edge, and now, or the edge ED, and now the edge CD is the last edge that has that property. And now we've included all vertices of the graph, so we have finished and we found a minimum spanning tree. So these minimum spanning trees are slightly different, just in whether they include AG or BG. So there are 2 different spanning trees in this case, slightly different, that are both minimum. You can prove that both of these algorithms will always select a minimum spanning tree, which is pretty incredible that these are both very simple algorithms, but they can be proven to always work.